Good morning, everyone. We are Team Lunar ROADSTER. Welcome to our SCD Encore. The team consists of me, Deepam, Ashwant, William, and Simpson. We are advised by Professor Ed Whitaker. The motivation for our project comes from the idea of the lunar polar highway. As we all know, humanity is returning to the moon, and a lot of these sites of interest are focused in the polar regions. The yellow line shows a path that could connect these polar regions, which circumnavigates the moon. What we're trying to answer is it possible for a rover to circumnavigate the moon without ever encountering the sunset? Why would you not want to encounter the sunset? Well, as you all know, the radiation and solar energy available on the moon is much higher than that on the Earth. So a rover that is solar powered could harness its energy and run for much longer than it would normally. However, if you think about it, on Earth, circumnavigation is not something that is easy to do. You would need very high speeds to make this possible. However, what helps us is one lunar day is equal to 28 Earth days, which means if you pick a latitude of, let's say, 80 degrees or 75 degrees, all you would need to do is go at a speed of 3 or 4 kilometers per hour to circumnavigate the moon. However, it is not that easy because the moon is not flat. So what we're proposing is a flat, circular, and traversable route that rovers with lower mobility capabilities could traverse. So our project, the Lunar ROADSTER, is an autonomous moon-working rover that is capable of finding these routes and grooming them to make them traversable. This is our primary use case. So if we take a reference altitude of, let's say, 80 degrees, this is what an original traversable path would look like, where you would have to avoid all of those craters and this path is very circuitous, not very circular, and it involves lots of twists and turns. Here comes our project Lunar ROADSTER. The first thing it will do is identify craters which are too big. So craters like that is something we would avoid, and identify craters which are small enough for us to groom. Using these metrics, we would create a new groomed path, which would end up looking like this, which is much more circular and would allow a robot to maintain something today's demonstration is divided into two parts: the pre-demo setup, which we will go into detail about getting the ROADSTER ready, setting up our environment, setting up external infrastructure, mapping out the environment, creating our transport goals, and planning optimal and manipulation. During the demo, we're going to switch to autonomous mode, follow the waypoints that we generate from our transport planner, and autonomously zoom this crater. We also have some fail-safes in place in case things go wrong.
Okay, the pre-demo setup. First, I will walk you through the hardware setup of our Lunar ROADSTER. Upfront, we have a custom designed closed assembly for efficient terrain manipulation. We have 4 3D printed wheels in order to maximize traction on loose, uneven sand like what we have here. On my far left, we have a Leica demonstration that continuously tracks this Leica prism. I'll talk about why we need this later on. The entire system is powered by 320-volt batteries, and the entire compute is carried out on the NVIDIA Jetson HGX CMU here. We have a weapon-nav IMU. We have a linear actuator to move the dorsal plate up and down. We have 4 motors, 2 in the front for drive and steer, and 2 in the rear for drive and steer again. And then we have the rest of the electronics neatly packed up in this electronics box. We also have a real sense that looks forward and we use this for validation. We are not doing active mapping this episode. So the Moonyard is our physical testing ground. We carved out a different crater from the SVD. So this will be the focus of today's grooming task. It's a kind of obstacle our bulldozer would encounter on the moon itself. So in order to give the ROADSTER a complete view of the environment, we map the terrain again using a Faro laser scanner. This device that you can see on the picture here gives us a very high density point cloud, which gives us a map which is used for the navigation and the two planning sections. So for the XY infrastructure, we have the Leica TS16 robotic orchestration that continuously tracks the Leica prism, and it gives us the XYZ coordinates related to a fixed frame. And we fix this frame over here. This is our map frame. So this is our X direction, this is our Y direction, and Z points vertically up. So the XYZ related to this is sent to the Jetson for localization using the TH2 relay, which is a box that you can see on the right hand side over there. And it does this using the LAN router. So as I mentioned, there is a fixed frame, and when we spawn it over in the Moonyard, we also calibrate its yaw so that the IMU readings are related to this fixed frame itself.
So using the point cloud that we obtained from the Faro scanner, we want to plan an optimal manipulation path that will be used to groom this crater. So we set up a cost function that minimizes transport volume and transport distance, meaning that we set up source and sink nodes essentially. Sync node is something that will be below our datum, or source node is something that will be above our datum. So for the creator, the middle of the creator is the sync node, and the outer rim of the creator is the source node. So what we're planning is a way to get the source nodes into the sync node to generate a flat datum. Using these transport assignments, we will then generate waypoints that the map planner will use to do the manipulation. Beginning with our demonstration. So what we will do is we'll turn the rover on and autonomously follow a straight path up to this rover and perform our manipulation. Our manipulation involves forward blading, where we'll be using the front of the blade as well as back blading, where we'll be using the back of the blade to give a finishing touch to the crater. This is our behavior tree. After we get the map, it is sent to our update map node, which then gives us an output saying the map has been explored. Then we plan the transport. The transport planner that I explained earlier. Using this, the get transport goals function will get generate waypoints sent to the app stack, and the goals remaining will also generate tool goals, which would tell us to move the tool up or down. After all of this is done, the mission will be end and the rover will stop.
Okay, so while the demo is starting, I'll talk a bit about our localization stack. So how does our rover know where it is relative to the myriad itself? So for this, we have three sensors. The LiGA total station gives us the XYZ values or the position relative to the map frame. We have the vector nav IMU, which gives us the linearly angled accelerations, and the encoders give us the mean velocities. So the data from the three goes into a global localization node. The data from the IMU and the encoders goes into a local localization node. Both of them run an extended Carnot filter, and ultimately they give out the pose of the rover, which is its position and the orientation relative to the map frame. So when the demo happens, I'd also like you to focus your attention to the screen on your right. On the visualization on the left, you can see the entire cost map. You can observe the crater and also the body frame of the rover itself. The arrows that you see are obtained from the tool panel. They are the goal poses, which are the targets for the navigation stack to act upon, and which further plans the path ahead. So I'll just walk you through the sequence of actions that will happen. Right now it's at the initial stage, and we'll move to an offset position, which is a certain distance away from the cable. From here, it goes to the source location, which is the beginning, the start of the cable, the region that has the most amount of sand, and it pushes the sand into the sink position, which is the deepest part of the cable and almost at the center. Once it does this, it's going to lift the blade up, then move to the other side of the cable, put the blade down, and backblade. So backblading is a novel feature that we implemented. It allows us to efficiently groom a crater in just two passes, a forward pass and a backward pass. We wouldn't have to encounter it from multiple directions as crater grading. So the demo still starting. So I'll talk about the navigation stack too. We have the navigation stack running in real time. The code goes obtained from the tool panel act as targets. And in the visualization, you can see, the plot in blue is a path obtained from the global navigation stack, and the plot in red is what the rover actually follows. So this is a grading video from a previous test run. We also showed this during SVD. And you can take up any questions that you can have.
What you're doing right now?
Is trying to start the planner.
It's not receiving the velocity.
Is it facing a few issues since yesterday? The audio has been reset.
It's not flashing.
Issues and mostly issues with the localization as well.
So yeah, we've been facing some issues that we weren't facing in SVD honestly. The Arduino just needs to be reset all the time. We haven't figured out why. But since yesterday, every time we started the rover, we had to reset the button about 4 times before it gets started. So while we wait for that, I can just play the video for you. Gonna move. Yeah, essentially the way it works is when we go to the offset, the reason we created an offset pose is we've been struggling to get the yaw right without an external input. So for the IMU, as we did the yaw calibration, but even then when the nav works, it kind of works. So we set up an offset pose which essentially allows us to allows us to align the yaw to an error, so that when it actually reaches the crater, it will be fine. That is why that's the offset for the page. And now you can see the backblading motion that we've implemented.
You mentioned you're doing yaw calibration with respect to the effect. Yeah, yes, the map frame fixed. So how you do that? So we do this initially in the freedom setup. We keep the rover oriented here so it faces this way. And we then use the average headings over like a certain window. We average it out and compare it to the actual heading, and then we apply that offset to every time heading for you. No. When you just spawn it gives a random yaw, so we have to wait for it. Move to the
Around enough, you have accumulated bunch of expansion. Why can't you figure out the law from that?
So we don't do AMCL for localization. That's the reason we don't move it around. The localization is just using the focus station and encoders and mapping.
Okay, audio reset. There's a reset button.
Is the location of the crater provided as a goal point here in the rover?
Yeah. So it's not a goal point, per se, but when we give the map to the rover, and then our transfer planner generates the waypoints. So we're not explicitly saying this is where the crater is, but it's going to identify the source and shape, and then plan accordingly as to what is an optimal path.
And then is there any step where it determines whether that's a crater or in its range to capability to grade versus avoid?
Yeah, I'll talk about that a little later.
Okay.
We essentially have a script that identifies whether it's greater or not.
Canceling? Okay, seems to be like we have some issues with the autonomous stuff. So this is the video we can show you and we can move on to that. If you can figure it out, we'll do it later. So basically what the rover capability demo is, we want to show you what the roadster is capable of, the mechanical capability, the electronic capability, the pushing power behind it, and what all reliability changes we've made to make sure that this is the proper machine that we don't need vectors. So beginning with, so while that gets set up, I'm going to show you some before and after pictures of where we got the roadster. So we got the rover and made it into the roadster. So when we got it, this is what it looked like, and this is what we have now. So the big changes are the wheels, a new electronic box, and a whole new tool, as well as we try to focus on making it look like a more finished and complete product. So for the stock, when we got the roadster, it has stock rubber wheels. These wheels rely on the interaction between sand and the rubber itself to generate friction, and that's how it gets traction. We moved on to some wheels which actually bend into the sand to generate the friction. So this we are able to generate more grip, giving us more traction. And we also up the actuation strength inside the drive itself. This allows us to actually gain more pushing power to actually create these craters. Otherwise, the previous one, as we increase the tool size, it won't be capable of pushing that much sand. The cluttered wiring that we had, that we got the rover with, this was the large form factor that we had. This not only we felt was not efficient enough, but it also led to issues with just wiring, loose jumpers. So we designed a compact e-box that has fixed position for everything. The wirings are stable and there are reliable connections. Further, we also designed a PCB. This PCB was before there were 2 terminals on it. Now this PCB we designed with RBP, OBP, and also XC60 terminals directly. So we have reliable connections as well as ease of assembly. This PCB has been fully integrated into the system, and that is what is powering the rover right now. Further, when the tool on the rover before was a central grader, the central grader allowed them more controls over the tool itself because the pitch was chassis average. And also, but they have to go into the grader completely to actually use the tool to its full potential. So now with the frontal dozer, we are able to increase the tool width significantly, as well as grade graders while maintaining all 4 wheels on the ground, which allows us to keep efficiency of speed in our system. That is our actual fall goal when we're grading multiple graders and creating a part. Are we ready?
No, not ready.
So we're still setting up teleoperation. Are there any questions with respect to the design?
don't have a question with respect to design, but I was wondering if you guys could highlight what's new since SVP.
Yeah, it's mainly the results section. So
Results section.
we can just talk about that. We'll come back to it.
Sure.
So these are some results in terms of the mechanical design, as I talked about, a better tool width, more actuators, and 3 times the tool width of the predecessor, double the torque, and we're able to get far greater pushing power, a reliable electronic system, as well as an efficient power distribution system. So this is an optimal specialized machine for grading these rotors, and we're
So I'll talk about the performance requirements. So our first performance requirement being that we will plan a path with a cumulative deviation of less than 25% from the chosen latitudes there. Since for SVD and for SVD Encore we tackle only a single crater and that only in a straight line, Okay, so sorry, we'll just move back to the teleoperation part. So our other rotor capabilities being teleoperation, those are operated become the demonstrators. We can wirelessly control it with the joystick. We can move the rover front and back. We can steer it left and right as well. We have active steering, so this allows us to control the front and the left steers, allowing us to make sharper turns as well. And this is very useful for traversing in uneven terrains like what we have here. Regarding the closing actuation stand, I demonstrate this by placing my foot directly beneath the dorsal plate, and when we push down, it's going to lift the front wheels up. This shows how strong the actuator is, and that's very important for efficient terrain manipulation. And in order to show the pushing strength and the crater grooming, we are going to groom this crater in front of it. So what we're going to do is we're going to move it closer to the source, the rim of the crater. We'll put the blade down. And so we basically configure the joystick so that every button press increments or decrements the dozer height by 5%. We push the sand, and then once it reaches the soap or the sink, we lift the blade up. We take it to the other side of the crater. We put the blade down, and then we backplate. We put the blade down, we backplate. Backplating allows us to efficiently groom this crater in just 2 passes. It was a little off, but it was not totally visible. Try again.
The adjustments made by the operator.
Yes, the adjustments are made.
I thought there was like a full behavior.
So we're not doing autonomous right now.
Okay.
Yeah. This was supposed to be for the autonomous, but we're facing issues. We changed to the operation. So just putting the sand back into the sink. So we begin the joystick. You can grade other craters by operating as well, and we'll move on to the other results.
yeah, we see these ones. You want to operate it around with it while we go about the experiment.
So I was talking about the performance requirements. Performance requirement 1. So our ideal path and the planned path would be the same. So this requirement is not applicable for us. For performance requirement 2, to show that the path followed by the rover is within the maximum deviation of 10%. So in the visualization, the plot in blue is what is obtained from the global navigation stack, and the plot in red is what the rover actually follows. We also calculate the per point distance, the gradient distance. We sum them up, and then we ultimately get the deviation. These were the deviations for multiple runs. Initially, we had deviations of 12.5%, 9.8%, and we, by tuning a lot of the navigation parameters, we were able to reduce it down to around 6. So this is the average deviation around 8.16%. So for performance requirement 4,
These were all straight line driving.
yes, this is all straight. So to show that we can avoid craters larger in size above 0.5 meters in diameter, we previously mapped the moonyard with multiple craters of varying diameters, one of which was a crater of size greater than 0.5 meters. We then had a script that would identify this large crater and then ultimately gave us the centers of only the gradable craters, which in our definition is a crater of less than 0.5 meter in diameter. So this is another visualization where which shows how the navigation stack treats a large obstacle as a large data as an obstacle and plans a path around it. We gave it a goalpost at a far off location, and then the plot in blue is what is obtained from the navigation stack, and the plot in red is what the rover actually follows. So it properly avoids the crater, although the shortest distance would just be a straight line through it. So going on next. Our performance requirements try to show that we can fill up craters up to 0.5 meter in diameter and 0.1 meter in depth. The craters over here are similar in size, and we can efficiently grade them. We also demonstrated this during SVD. So this is our before and the after. A few metrics for this. We use the real sense for validation. We just take snapshots of it before and after. So the figure on the left shows the before grooming, and on the right shows after grooming. We then obtain the height map of this. So for the before, the mean elevation was 1.41 centimeters, and after grooming it reduced down to 0.99 centimeters. And the elevation RMSE before it was 2.91 centimeters, and after grooming went down to 1.9 centimeters.
And Vinny, you had asked us how we're planning to make the Moonyard more lunar accurate. So the work we've done on this is using raw data from the Robbins 2018 data set. We were able to generate a PDF and a CDF to identify the crater sizes and the crater distribution. Based on this, we simulated certain parts of the Moonyard, and the one key assumption we did make is that the craters have to be between 0.1 and 2.5 meters so that they fit in the Moonyard. So we're able to generate some simulations of what an accurate lunar picture in the Moonyard would look like, which is what we'll be doing at PDU. So majority of this work is actually attributed to the Moonshot Circumnavigation team that was part of Professor Ed's space robotics course, and William adapted it to our project, and then we're able to use it.
Yeah, so we are ready to join our fellow rovers Moon Ranger in the Artemis missions to colonize the Moon. So thank you very much, everyone. We are Team Lunar ROADSTER, and we can take up any questions that you may have.
Go back one slide. What you just showed. So did you say that you use something like this simulated configuration to produce?
Today? No, not today.
Okay.
So we just picked one crater, but we showed you a previous map with multiple craters and plots that are obtained from this.
Right. Yeah, that'd be good. But I was wondering, what are you going to do, if anything, with that simulated configuration? That's something for FET?
Yes, right. So we cannot show multiple craters.
Yeah, so we want to set up an environment like this in the Moonyard, and then run our stack on that to see.
And what's the size of the biggest one on the right?
That's 2 meters. So we'll make assumptions and see what is possible for us to create in that.
Now, it seems like, I don't know if it was EPOM's varying of the tool, the dosing tool, but as it was coming back, it was kind of varying its height somewhere. But my general question is,
I didn't hear that, John.
yeah, it seemed like the tool was varying in height when they were doing the back.
Very.
Yeah, varying in height. So, but I was wondering, are you going to face problems? I know you guys are going to apply your algorithm and you'll have feedback and understand better to what degree they're going to be filling. But are there going to be geometric issues with actually getting that low enough? Or it's going to be able to do everything to make flat grades, basically. We were backing up.
You're backing up. That's why I asked about the behavior. Because I thought you had a pattern there. You push the pattern, it does something.
So when I was backing up, the rover pitches forward and backward. And so when I back up, I always do the resonate.
But it was a tool. It was a tool that was going on.
Yeah, that's right.
Okay, so that's one of the problem we are facing is that in an intermediate position between the components and the body. The PID is not linear.
That's what you talked about before, the jitter. I see.
Yeah, so it's jittering.
Yeah, of course. But in that case, I mean, at least for this particular backing up, probably would be better to just have it all the way in the down position in order to actually smooth it. But the general question is, are you going to be able to do what you need to do?
Yeah, right. We have plans of mitigating that. We have different kind of actuator also that we can try which we can do away with the iron also. I don't know. side given. We have plans.
Okay, and then last question for you is, I know you had the Arduino reset issue, but do you have a feel for what's going on with the autonomy? Is that the only issue right now?
Yeah, it is. So it becomes a sort of a bottleneck. Like all of the stuff is going to the website, everything's working properly, but then it doesn't receive the feedback it needs from the Arduino, so it kind of shuts down. And then when we reset it, starts up again. It's just like a balance that is not working out at the moment. And we'll figure something out with creating specific sequences for that so it doesn't happen.
One more reason that we happening with that, like last week we are running the other things. So, and we are facing some lags on the that we probably upgrade to a different.
Other questions?
Is there a method for flatness or is there a performance requirement? Because now looking at this, like if you look at the bug you just filled manually, someone's filled the bug manually, you see that you have now created a bit of like unevenness to the side compared to it just flat. So how do you define that flatness? And like, of course, you change the wheels as well now. And so if you were to ask anyone, like in terms of flatness, what do you consider this to be flat, or do you think for the final validation that we change
So we're tracking two metrics. One of them we'll say is that the maximum traversable slope that our rover can do, we're assuming it's much better than what other lunar rovers can do. So we're going to assume a maximum 5-degree slope as validation of it. So anything that's above a 5-degree slope, we will call that we should do it again. As well as just to see how it would be our quality, we're going to be tracking RMSE height metric. So we have a datum that goes to the center of the crater that matches the other part of the moon yard, and then calculate an RMSE error. So on this slide, I'm not sure it's quite visible, but we're actually reducing that RMSE error, and that's what we're tracking as well.
Sorry, I still have I don't have clarity on the planning and obstacle avoidance. It's okay. Is the obstacle avoidance done reactively in a local sense or not? Right? You look at the big map, and then plans, and then the robot base avoids there, then the robot base can fall there.
Yeah, since we don't have dynamic obstacles, we're not actually planning on doing anything locally for obstacle avoidance. Our moon yard is pretty defined. We know where the unbeatable cases are. We don't need a very robust local planner to avoid obstacles. Okay.
Following up on Timmy's question, do you avoid the like ungradable craters, but do you make sure that you go through the gradable craters in the trajectory?
Yeah, so that's again because it was only one crater today. We could show that, but yeah, that isn't part of the plan. That once we have a full global path, so here we just try to show you that we can avoid obstacles. But then when we generate a circular plan, we go through the gradable crater.
So you do update the global. Once you create a crater, you update the plan.
The plan?
Yes, like kind of the overall picture, so to speak, that then the robot can move around.
Currently, since we can't have a map right now because we're using the parallel scan map. But next time when we use the real time properly in the local system, then we'll be able to update the map. Yeah.
You encounter any scenarios where the blade maybe gets like too much material in front and it gets stuck and there's too much like reaction force for the wheels to overcome?
Yeah, so one issue that we face is when the rover itself actually pitches. We tune the closer heights to a point where we're confident it's going to do it. But if there is a hill and we go down that hill, then that height changes and they're actually being into the ground. When that starts happening, then yes, we do face problems. It's not being able to push and solve it. So when that happens, we just try to move back, and try and push the work over it, then push the tool down again.
We have like detecting that that's happening.
So we plan to integrate like a load cell in the front of the blade. Haven't done that yet. Haven't needed to do that yet because we don't have like very deep craters with it. But if we do need it next time, that is something that we might
Have you considered current sensing of your load or torque?
Yeah, that's a great study. We'll do load cell on that, or basically solve that with the user.
Load cell for torque?
Load cell on the front of the blade, not the top. So to get
I'm asking about a wheel, a torque. Are you considering the actuator for propulsion that would just give you a current readout.
Yeah, so I think earlier that the activities that we're trying to change, we are thinking of getting one which has the ability where we can read the current value. So if it's pushing more sand than it's pushing, and it gets all, the current shoots up greater than the threshold we get.
We've heard a few of these. Would you just summarize the mechanical, the mechatronic upgrades that are yet to be seen?
They are mostly towards the closer activation.
Number one is what?
The closer activation. So either like firstly we try to fix the jitter. Secondly, we want some kind of feedback on this stalling. So it's all related to the closer activation. We can translate that to the decoder as well. Like if it starts stalling, the encoders give us the rotation values, but those are not correct also. So we try to see if we can get the kind of information.
I'm sorry to interrupt. We're gonna have to run because we're getting to the next team.
Next demo. Yeah. Okay. Thank you, guys. Thank you.